Okay, let's dive right into this explainer and demystify the absolute mechanical marvel that powers our modern world. We're going to look closely at something most of us rely on literally every single day, yet kind of take for granted, right? Like what actually happens under the hood when you turn the key? We rarely think about it during our morning commute, but the answer is this fascinating synchronized chaos. I'm talking thousands of tiny, perfectly timed explosions happening every single minute, just a few feet away from where you're sitting. To truly wrap our heads around this, we're going to decode the information from a massive 400-page engineering textbook, Engineering Fundamentals of the Internal Combustion Engine, and distill it down into a simple, step-by-step anatomical journey. We'll pull in insights from actual technical manuals too, so we can see exactly how these machines wake up and operate. But before we zoom in on the nuts and bolts, let's take a quick breeze through the history that made modern engines a reality. The engine didn't just pop up overnight. Back in 1860, the Lenora engine gave us a very early, kind of practical design. Then by 1876, Otto developed the four-stroke cycle, which is literally the foundational breathing pattern of the car sitting in your driveway right now. And here's a wild fact for you. In 1888, John Dunlop invented the pneumatic rubber tire. That is what actually made cars comfortable enough to drive, kicking off a massive boom in the engine's popularity. Shortly after that, in 1892, Rudolf Diesel perfected his super-efficient compression ignition engine. Section 1. Turning the starter key. Awakening the machine. So, our journey starts right at the ignition switch. An engine can't just start on its own, right? It has to be physically spun to take that very first gulp of air and fuel. To make that happen, we need a massive surge of electricity from the car's battery to spin the resting engine. But here's the catch. The starter motor needs a huge, heavy electrical current. If we ran wires thick enough to carry that kind of juice all the way up to your steering column, yeah, it'd be incredibly dangerous and cause violent sparking right at your fingertips. No thanks. So, because the starter draws such heavy current, we use a solenoid. It's this clever little electromagnet switch. When you turn the key, a tiny, totally safe current goes to the solenoid, which then magnetically pulls a heavy iron rod to safely close the massive electrical circuit down at the starter motor. And because of all that intense power, the way the starter connects to the engine has really evolved over the years. Older cars used what's called an inertia starter. When the motor spun, this Bendix gear would just violently travel down a threaded shaft and basically smash into the engine's flywheel. It was super abrupt and caused heavy wear and tear. But today, modern cars use a pre-engaged starter. That same solenoid we just talked about uses a sliding fork to gently, and I mean much more gently, push the gear into place first, and only then does it send the massive current to turn the engine. It seriously saves our gears from so much unnecessary wear. Section 2. Anatomy of an engine. The components of combustion. Now that the starter has the engine turning, let's zoom in and explore the actual physical layout of the engine block itself. This is where the magic happens. Depending on how much space they have and how much power is needed, engineers arrange the cylinders in some pretty fascinating geometric shapes. You've got the common inline design, where cylinders sit in a straight row. Then there's the V engine, like your classic V6 or V8, where two banks of cylinders sit at a 60 to 90 degree angle to save space under the hood. There's also opposed flat engines, which you'll often see in small aircraft, the super rare W engine with 3 banks built for racing, and the massive radial engines, where cylinders form a literal circle around the center. That's the iconic design you'd see on vintage propeller airplanes. Section 3, the four-stroke cycle, the breathing metaphor. Once it's running, the engine sustains its own movement by acting almost like a living, breathing organism. We call this the four-stroke cycle. First up is intake. The piston moves down, creating a vacuum that literally inhales a mixture of air and fuel. Second is compression. The piston moves back up, giving that mixture a high-pressure squeeze. Third is power. The spark plug fires, setting off a massive explosion that forces the piston down violently. This is the stroke that actually pushes your car forward. And finally, the exhaust stroke. The piston pushes back up, acting just like a lung exhaling the spent hot gases. Inhale, squeeze, bang, blow. Now, there's a fundamental difference in how we actually trigger that bang depending on the fuel you're using. Standard gasoline engines use spark ignition. They rely on a high-voltage spark plug to ignite the mixture. But diesel engines, they use compression ignition. Get this, they don't even have spark plugs. Instead, diesel engines compress the air so intensely at such crazy high pressure that the fuel just self-ignites from the extreme heat of the compressed air alone. It's wild. Section 4. Power, torque, and output. Measuring the muscle. With rapid explosions happening thousands of times every single minute, we've got to measure the physical force that actually makes it down to the vehicle's wheels. See, not all the raw power generated inside the cylinder actually reaches the road. Engineers use a term called brake work. Think of it like this. Your engine has to pay a tax just to run itself. To find our true brake work, we take the raw energy of the combustion and we subtract internal friction plus all the parasitic loads the engine powers, like spinning its own oil pump, the water pump, the alternator, the AC, whatever's left over. That is your brake work. And when we look at how that power is actually delivered, check out the power and torque curves of a heavy-duty GM 7.4-liter V8 truck engine. Notice how the torque, which is that raw twisting force, peaks at lower engine speeds, around 3,200 RPM. That's not an accident. It's designed deliberately to get a massive, heavy truck moving from a dead stop. But maximum horsepower, which is what dictates your top speed, requires much higher engine speeds, so it peaks much later on the graph. Just to highlight a crazy extreme from our sources, engine speeds can go way, way higher than a typical truck. Back in the early 90s, Honda built a customized racing motorcycle engine that featured oblong cylinders and 8 valves per cylinder. This absolute engineering marvel hit a staggering 14,000 RPM, churning out an unbelievable 130 kilowatts per liter of displacement. It just goes to show how pushing airflow and engine speed limits can generate massive, massive power. Section 5. Exhaust, emissions, and noise, the aftermath. To wrap up our anatomical journey, let's look at the 4 main exhaust emissions that environmental laws and modern engineering have worked tirelessly to control over the last few decades. First, hydrocarbons, which are essentially just unburned fuel escaping. Second, carbon monoxide, which happens when there isn't enough oxygen to fully burn the fuel. Third, oxides of nitrogen, or NOx. These are actually created because the extreme temperatures inside the engine cause normally stable nitrogen in the air to break down and react. And finally, solid particulates. That's the black soot you commonly associate with heavy diesel engines. Thankfully, we don't just vent these directly into the air anymore. Thanks to after-treatment devices like catalytic converters situated in the exhaust system, we can chemically strip these harmful emissions down into basic water, carbon dioxide, and nitrogen before they ever leave the vehicle. It's literally a high-temperature chemical laboratory operating right under your floorboards. And we haven't just engineered the emissions away, we've engineered the noise away too. Modern cars use passive abatement, like stiff, ribbed composite materials to block sound. They use semi-active, fluid-filled hydraulic engine mounts that actually change viscosity to absorb vibrations. But the most amazing part? Some modern cars use futuristic, active anti-noise cancellation. Sensors read the frequency of the engine noise, and speakers actually play an inverted, perfectly out-of-phase sound wave into the cabin to literally cancel out and silence the engine. How cool is that? From the clever little solenoid engaging the starter to the 4-stroke breathing cycle, all the way to the chemical laboratory hiding in the exhaust pipe, it truly is a marvel of modern engineering. So next time you turn the key, will you just blindly drive away? Or will you take a second to appreciate the synchronized chaos of thousands of explosions per minute happening right in front of you? Keep learning, and I'll catch you in the next explainer.